So today, our last session, and our speaker is Dr. Sunil Matthews. He's an associate professor in the Department of Mathematics at the National Institute of Technology, Calicut. His research expertise spans biocomputational modeling, cancer detection research, fractals and chaos, graph theory, and fussy graph theory. In fractal geometry, specifically, his work focuses on various types of iterated function system, their attractors, and aspect of chaos theory. So it's a pleasure to have you, sir, and we invite you to begin.
Thank you, Harsha, for the introduction. So shall I begin?
Yes,
Yes,
sir.
Thank you. So good morning to everyone. Today, as mentioned by Harsha, I'm going to discuss about iterated function systems on product metric space. And few of their properties, like separation properties, also will be discussed. Yes. Yes. I'm not sure about the anatomy of the audience, so just in few slides, I would like to give the fundamental details of fuzzy graphs only in few slides for those who are not good in the fundamentals of fractal geometry. And as all of us know, classical geometry, especially Euclidean geometry, was dealing with shapes with smooth edges like circles, parabolas, etc. And that study continued for a long period actually. But only recently, as you know, Professor Benoit Mandelbrot introduced a new geometry called fractal geometry that was almost similar to the geometry of the nature. So we can consider Mandelbrot as the father of fractal geometry. Of course, it is an extension of ordinary geometry because, for geometric objects, the results will remain true. And today, a few names are very important for us. As I told you, we'll be focusing on self-similar sets, sub-self-similar sets, super self-similar sets, etc. So the father of self-similarity in some sense was Johnny Hutchinson. You know that he introduced self-similarity in 1991. And he only introduced the concept of iterated function systems as a way to produce fractals in a mathematical setup. And we need to mention a few more names here. So when we study iterated function systems, some very special kind of systems like condensation iterated function systems are very important. So these two people, Michael Bansley and Stephen Demko, introduced condensation IFSs in 1985. And this Faulkner also is very, very important for us because the concept of super and sub self-similarities and their properties were studied for the first time by Kenneth Faulkner in 1995. Anyway, let me start with the fundamentals again, because when we discuss the dimensions of subsimilar, etc., we need these concepts. So I really hope that many in the audience may be well aware about these basic definitions: Hausdorff outer measure and Hausdorff measure. And using Hausdorff measure, you can go to the definition of a fractal. Of course, topological dimension also are well aware of. You know what is exactly meant by topological dimension of a set. Anyway, being the very fundamentals, I'm not going to repeat them again. They are available in the slides. So, as a fundamental definition of a fractal, we can use this. Fractals are such for which Hausdorff dimension strictly exceeds its topological dimension. You know that also is not a Niefenreuil definition because there are fractals whose Hausdorff dimension exactly equals to the topological dimension. Okay. So anyway, we will consider this one as the definition of fractals. On cost curve, its topological dimension is 1, whereas its Hausdorff dimension is 1.2 something. That's why we can call this fellow as a fractal. And fractals are also recognized by means of their properties. You know that, for example, the self-similarity is a very nice property when we comes to the nature and other objects in nature. And infinite details, you know that when we deal with nowhere differentiable functions, that will exhibit infinite details. And of course, when you deal with classical examples like one cos, etc., you will be having infinite lengths. That's another infinite area, etc. And the Hausdorff dimension will be fractional. So all these things we have. As I told you, these are not if and only if, because there are fractals like Mandelbrot set, where its topological dimension and Hausdorff dimensions are integers. So it is violating one of the conditions. So, but anyway, we will proceed with our definition. These are the properties of fractals. And mathematically, you have plenty of ways to generate fractals. And we have plenty of different disciplines also available in the fractal geometry domain nowadays, like complex dynamics, chaotic dynamic systems, Brownian motion, etc., etc. But we will be focusing on the very classical version of iterated function systems. Okay. So again, from some fundamentals anyway, those who are experts in fractal geometry may be well aware about these definitions, but we'll have a quick revision of those kind of things. For example, Hausdorff metric is very important for us. Distance between two convex sets generally we calculate. So this is how the distance between, two sets A and B are calculated in a metric space. And of course, the definition of contraction mappings, a transformation is said to be a contraction if we can find a parametric value between 0 and 1 satisfying this property, you know, all those things. So, and this is called the contractivity factor. And when equality holds there, it is called a contracting similarity. All these ideas are very fundamental. Again, this is how, say, the IFS was introduced for the first time. A complete metric space together with a collection of contractions. And all these contractions will have contractivity factors also. Their maximum will be considered as the contractivity of the system itself. For example, R is given with along with two contractions, S1 and S2. So they can produce, you can see the output is very clear and trivial from this. You are all well aware about that. Now, along with ordinary set of contraction mappings, if you add something like a constant, see a transformation of this kind, S naught of B is equal to C, whatever B is given as input, it's a condensation mapping. Even though it looks very simple, it has immense consequences in the study of attractors and IFSs. And in homogeneous, of course, that's condensation IFS is actually a few of the, majority of the works, in this work are done by one of my research students, Ashwati, and she has produced wonderful papers in this field, and she has produced several new concepts also. So, suppose you have a hyperbolic IFS with contractivity factor X and a condensation mapping also. You put the condensation inside, you'll get a IFS with condensation or an inhomogeneous IFS. That's another name. And we have the basic theorem by Hutchinson, you know that, see this W defined as union of SIH, and this mapping will have an attractor, will have a fixed point, and that fixed point is co-attractor. All these stories are very, very fundamental. So using this theorem, we will think about attractors of hyperbolic iterated function systems. Very classical examples will be provided. You can see R2 is taken, some 1, 2, 3, 3 contraction mappings are provided, and this is what is the set we are starting with, a filled rectangle, and one map will take the rectangle to the top, one to the left, and one to the right. So you can see the second picture, and the process will be continued, and finally you will land with the required attraction. So that is what is the basic idea. So you can see that. And the concept of cell similarity is like this. A set is cell similar for the contracting similarities SS12 is A is equal to U SIA. If you can express the set itself is a union of its own copies, it becomes cell similar. The Cantor set is cell similar for this for these contractions. S1x is x by 3 and S2x equal to x plus 2 by 3. It's a very simple example for a cell similar set. And of course, anyway, that they are representations only. Again, super cell similar means a set is super cell similar if the set contains the union of its copies. So as SI is your contractions, when we apply them on the set, you will get several copies of different scaled versions. The union will, you can see A contains the union. Okay. And if that containment is strict, we call it strictly super cell similar. Otherwise, it is simply super cell similar. We have examples here. You can think like this. You can see the copies are there are many copies and they are similar to the entire set, and the definition follows from here. So this is an example. S1, S2, S3, S4 are provided here. The union you can take and the set is already inside. Subcell similar is also defined in a similar fashion. Only thing is A must be a subset of the union. So it is exactly similar actually. Here we call it a strictly subcell similar if the containment is strict, if the inclusion is strict. And examples, they are very simple examples. 0, 1 is strictly subcell similar for two transformations. S1x equal to x by 2 and S2x equal to 3x plus by 2. By 4, you may just take the images, take the union and see what is the relation between the set and the union. And of course, contracting subcell similarity and contracting supercell similarity. If a contracting similarity is a contracting sub-similarity, if it maps the points of A to the points to A itself. When S takes A into A, it is called contracting sub-similarity. Example is x equal to x by 2. You know that 0, 1 will be going to 0 half. So it is contracting sub-similarity. And the rest of the works are from this particular paper, and that was published in 2016 on different forms of cell similarity. I mean, a few of the next slides. And you can see with these two contractions how we produce, same sets for two different starting seeds. You have a discussion of this very quickly. And of course, union, we will wonder in this presentation whether the union of two supercells is a supercell similar set, or what will be the structure of that. You can see that that is not going to be a supercell similar. It's neither cell similar nor supercell similar. See that A is the effect of S1 and S2, B is the effect of S1, S2, S3, S4. We are getting two supercell similar sets, but their union is anyway motivated by this. We will have some results to follow. It's not subcell similar either. So our first result is the characterization of supercell similar sets. A non-empty compact subset of X is A is supercell similar for this set of contractions, if and only if each SI is a contracting subsimilarity for A. That is almost obvious actually, it's not a big theorem. If all of them are contracting subset similarities, it becomes a supercell similar set. And in a complete metric space with two or more elements, non-supercell similar sets are dense in the set of all closed and bounded subsets of X. Similarly, cell similarity, supercell similarity, and subcell similarity are preserved under isometric maps. And this is, suppose we have a complete metric space, a non-empty closed and bounded set A cell similar for the contracting families. That is our assumption. Then product of A is supercell similar in product of H with this particular metric. D dot is equal to maximum distance between xi and yi. So this particular metric, where they are vectors in this product space. So if A actually is cell similar, then the power, or we can call it as A power n, is also supercell similar in the product space. So if something is supercell similar in R or R2, you take the powers, you can see their products also become supercell similar. And yeah, there are examples. These are examples of supercell similar sets. Yeah, two types are available in the slides. Anyway, you can go through it. Now, we'll come to another kind of supercell similar set called exact supercell similar set. A set is said to be exact supercell similar if it is strictly supercell similar for a set of contracting similarities, but never cell similar for any set of contracting similarities. It's an interesting kind of sets. This is an example. Look at this. This S1 is equal to this, S2 is equal to this. When we apply on the triangle, we will get this Sierpinski like this. You may have a close look at these examples yourself, and this will satisfy the properties. Exact subcell similar is another one. A is said to be exact subcell similar if it's strictly subcell similar for a set of contracting similarities, but never cell similar for any set of contracting similarities. Here we have an example. There are 9 such mappings. You can, but it will take a little bit of time to verify that none of the subsets will form a cell similar sets. Now we have another one, optimal condensation IFS. And a condensation IFS, okay, with the condensation set C, of course, is optimal if and only if its attractor is different from that of X1, X2, S. Okay, S0 is our condensation map. If they differ, we call it as an optimal condensation IFS. Look at the example. R S0, S1X, S2X. Condensation set is 1, 2. So S0 of 1, 2 is 1, 2 itself. When we add it, you will get one attractor. If you remove it, you will get another attractor. Okay. So that's why this becomes an optimal condensation IFS. And there is minimal condensation IFS also. A condensation IFS condensation is minimal if its attractor is different from any of its sub-IFSs. So you may think about sub-IFSs. Their attractors also can be considered. If all of them are different, we can call it a minimal condensation IFS. Here is an example. S1 is x by 2, S2 is x S1 plus by 2. Condensation set is 1, 2. You may verify that the attractors we obtained when we restrict the condensation, the set are all different. You can see that. So we can verify yourself. Next is a characterization. A set is strictly supercell similar for some finite set of contracting similarities if and only if there is an optimal condensation IFS with attractor A. The proofs are not provided here. If somebody is interested, I can send you the papers and you may go through the proof. And if a set is exact supercell similar, there is an optimal condensation IFS with attractor A. That's a consequence of the theorem 1.5. And of course, such an optimal condensation IFS is not unique actually. Look at this is S1, S2, S3. They will produce this, and you can go to using another set of contractions also. You can go, so they are not, the IFS are not unique. Now, the attractor A of an optimal condensation IFS of contracting similarities with condensation set C is exact supercell similar if there is no finite set of contracting similarities satisfying this condition. So that our C condensation set is union of Si dash A. Si dashes are from X to X. If you cannot find a set of contracting similarities, which gives our condensation set as an attractor, that is what is meant in the last line. Then in that case, then the attractor will become exact supercell similar. It's a very interesting result. Please go through the proof of this. And let X be a minimal condensation IFS. Any sub-IFS is also minimal. And attractors of all sub-IFS are strictly subcell similar for the set of contractions S1, S2, etc., Sn. So there is another question. Can an exact supercell similar set be exact subcell similar? You can see we will answer this question in the next theorem. Also, is it true for all exact supercell similar sets? That's another question. So they are answered in the following theorems. An exact supercell similar set is also an exact subcell similar set if there is an optimal condensation IFS generating A having a subcell similar condensation set. Similarly, it's an interesting result that C and be a sequence of non-empty closed and bounded sets. Look at this. Non-empty closed and bounded sets which converges to some C in Kx. this circular portion is our condensation set. Actually, there's a sequence of sets converging to that. They are all closed and bounded sets. Okay, in that case, and at A and B, the attractor of the condensation IFS yn. You can take each of these singular elements in the sequence and proceed for the step by step. We can go and find the condensation IFS yns. You will get okay, similarities will be S1, S2, S3, Sm, and contractility factor will be S. Then the sequence An converges to A. Attractor of the IFS phi with the condensate set C and contractility similarities S1, S2, Sm. Okay, so you may be good in that continuity theorem actually. Okay, you can see a similarity here also. Yes, this one also. Look at these are all attractors actually. Look at this. These are the sequential attractors, and they also converge. That's the meaning. So one by this sequence also converge the endpoint. Okay, so exact super self-similar sets are dense in the set of self-similar sets. You may have seen several results very similar to this in fractal geometry. We have a corollary data with a set of all exact super self-similar sets, which are super self-similar for the set of contracting similarities S1, S2, Sm. Then the self-similar set E with respect to these contracting similarities can be obtained as intersection of A from delta. It's a consequence because of this denseness. You can easily write this corollary. Another corollary is strictly super self-similar sets are dense in the set of all self-similar sets. Similarly, exact super self-similar sets are dense in case Rn. Actually, now we will discuss a little bit about separation properties of these homogeneous IFSs. They are all, these results are from the separation properties of finite production of hyperbolic IFSs, published in Communications in Non-Science and Numerical Simulation. All of you may be well aware about the code space of with an IFS. Okay, so there is no need to repeat it again. With regard to this metric, we can define the code space and this mapping also. So you have this is available in Barnes-Lee's textbook also. From the code space to the attractor, there is a continuous mapping, and it's an on to also. You might have gone through this continuous function connecting code space and the attractor of an IFS. And the code space also depends on the number of contraction mappings in the iterative function system. Okay, and there will be a set of addresses to every element in the attractor. Phi inverse A is equal to set of all sigma, so that phi of sigma is equal to A. So they are called set of address of A in A. And many may be aware about these separation properties. So an IFS is said to be totally disconnected if each point of its attractor possesses a unique address. And just touching if it is not totally disconnected but satisfy open set condition. And overlapping if it's neither totally disconnected nor just touching. And this definition also, definition of similarity definition is also required here. Let X be hyperbolic IFS with attractor A, and each SI is a contracting similarity with contractility factor SI. Then the similarity dimension of the set A is a unique positive real number satisfying this condition. Sigma I equal to 1 to M SA power alpha equal to 1. You know this definition. Candidate set of similarity dimension equal to that box counting dimension 0.631. You know that star very well. And similarity boundary of set is defined like this. Suppose you have an IFS, S1, S2, S3, Sm are the attractors. Similarity boundary denoted by this symbol is defined as, say, union Si inverse of SAA intersection SJA. And this is inverse invariant if this condition is satisfied. Example, A equal to 0, 1 is self-similar for S1 x equal to x by 2 and S2 x equal to x plus 1 by 2. So its similarity boundary is element 0, 1. And you know that that's essentially the topological boundary of that set. Okay. Here you can look at this S1, S2, S3, S4. They are 4 mappings. So these are the, see, look at this, the boundary point. Actually, they're bound the boundary. That is it. So S1K, S2K, they are sharing points. They belong to the, yeah, you can go through the definition. An IFS is said to satisfy open set condition if they resist an open set U such that Si of O is a subset of O for every I, and SIO intersection SJO equal to phi. So in that Sierpinski triangle, you might have seen when you apply a function to the rectangle, it will one function will take it to the left, one to the left, and one to the right, and you can draw an open, a circular region satisfying this condition. Si of O is inside O and SIO intersection SJO are equal to phi. So that satisfies open set condition. You know that. It becomes a strong open set condition when that attractor intersection is empty. And one more is their strong open set condition in AA. That is, there exists an open set O subset A such that Si of O is subset O and their intersections are empty. So it may be good in these kind of things. So using these, let A be the attractor of an IFS with similar dimension alpha and Hausdorff dimension K in the Euclidean space, then SOSE if and only if OSE if and only if its dimension is greater than 0. These concepts are all equal. That will imply that K is equal to alpha. Now, let A be the attractor of an IFS with similar dimension alpha and Hausdorff dimension K in a general complete metric space. Then its SOSE is equal to, implies K is equal to alpha. Similarly, let A be the attractor of an IFS with similarity dimension alpha and Hausdorff dimension K in a general complete metric space. Let B be the similarity boundary of A. If the similarity boundary is inverse invariant, then this condition is satisfied. And Vygotsky dimension, you may be aware about this. It becomes box counting in other metric spaces. So the definition may be aware to you, very well-known definition. Logarithm of n epsilon A divided by logarithm of 1 by epsilon. When you cover the particular attractor with bolts of red side 1 by epsilon, you count number of bolts and take the ratio, you will get it. So that's also required for the next. So let A be a non-empty compact subset. This is already existing result. Then dimension, Hausdorff dimension is less than or equal to this Vygotsky's dimension. And we are going to some product spaces and see the dimension business. The product of two IFS, you take the products of phi and psi. We will denote it by phi cross psi. And that is defined as, see, contractions will be the products actually. Sij equal to Si cross Sj star. 1 less than or equal to I less than or equal to M phi and 1 less than or equal to J less than or equal to M psi. And if A phi and A psi are attracted, it's a phi and psi. A phi cross psi, that is the attractor of phi cross psi. That coincides with A phi cross A psi. Very interesting result. Because I will tell you one thing here actually. Why we have introduced this product is, there was a study, even though physicians do not like the study of tumors using images, there was a study with the scanned images. We tried to reproduce a tumor using a scanned biopsy, scanned image of a tumor from different directions, maybe from different dimensions indeed. And that situation, in order to produce the 3D tumor, see, what we have to do is, anyway, with some error at the least, you take one scan, use Collat's theorem to make the attractor generating that particular image with an error. And of course, we have seen before, if it is similar, their product will be, etc., etc. Anyway, in order to generate, you need to consider a tumor will look very different from different dimensions. So your IFS also may be different in these 3 dimensions. But you are aware about the attractors. So take the product of these IFSs and think about the attractor of the product IFS. And this theorem says that will be coinciding with A phi cross Si. So this is a really good result with regard to applications. And not only our work, there are a lot of people doing a lot of work using, in applied field using this kind of results. Okay. And separation properties of homogeneous product IFSs. Suppose you have 2 product IFSs. They are homogeneous indeed. Then the product phi cross psi is totally disconnected if and only if phi and psi are totally disconnected. Not a deep theorem, but still very important. So clearly, finite powers of totally disconnected homogeneous IFS are totally disconnected. That corollary is interesting. And totally disconnected homogeneous IFSs satisfy strong open set condition, SOS. And that phi is equal to this S1, S2, Sm. of course, m phi, and psi equal to y s1 star, s2 star, s m psi star. Suppose they are two homogeneous IFSs. The product phi cross psi is just touching if and only if any one of the following holds. First condition is both phi and psi are just touching. Two, phi is just touching and psi is totally disconnected. And psi is just touching and phi is totally disconnected. So this is an interesting result. The product is just touching if and only if any of these three holds. Now, suppose we have two IFSs, phi and psi. They are homogeneous. The product satisfies strong open set condition if and only if both of them satisfy strong open set conditions. Similarly, the product is overlapping if and only if at least one of phi and psi is overlapping. And suppose we have two IFSs and both of them are homogeneous, and we look at the individual attractors and the product attractors. Fi, Si are the individual attractors. Phi cross I is the attractor of the cross product of the iterated function systems. The product satisfies strong open set condition if both phi and psi satisfy open set condition in A phi and A phi dash respectively. The product satisfies strong open set condition in phi cross I if both phi and psi satisfy strong open set condition in A phi and A psi. That is this. Now, there is one more type of homogeneous IFS and product matrix space, type 1 homogeneous IFSs. So you look at this, a homogeneous IFS on the product matrix space, X cross Y maybe, for simplicity we take only 2, is type 1 if each contracting similarity Si is of the form Si of xy is equal to Si1x, Si2x, where Si1 and Si2 are contracting similarities on x and y respectively, but it is not the product of any two IFSs. Okay, so this on the product, this is said to be type 1 if the each contracting similarity Si is of this form. But it is not the product of any two iterated function systems. So that's the definition. Now, suppose phi be a type 1 homogeneous IFS on X cross phi with attractor A. The attractor of this, you can see from the previous, these are the names given for this pi 1 of phi and pi 2 of psi are the names given for this type 1 iterated function systems. Okay, so the attractor of pi 1 phi cross pi 2 phi, attractor of the product of those two IFSs, we denote it as A pi 1 phi cross pi 2 phi, strictly contains J. That will be strictly containing the set A. Now, let phi is equal to X cross Y. Let us go to the, in the product space again. Be a type 1 homogeneous IFS on X cross Y with attractor A. Then, if pi 1 phi cross pi 2 phi is totally disconnected, so is phi. So there is a relationship between them. Pi 1 phi cross pi 2 phi is totally disconnected, so is phi. The converse is not true. Even if this pi 1 phi, okay, if phi is totally disconnected, then pi 1 phi cross pi 2 phi need not be totally disconnected. This is an example. This is an example of a totally disconnected attractor. So maybe phi is this. Phi R2 is in picture is in R2, and they have 3 contractions. Okay, this is clearly totally disconnected. Look at this pi 1 phi and pi 2 phi. Pi 1 phi will be, so it is in the, as you know, it's projected 1. So R will be x by 3, x plus 1 by 3, and x plus 2 by 3. Okay, and second one is x by, anyway, we are removing that y portion, y by 3, x by 3, x plus 2 by 3, right? Because y by 3 repeating 2 times. So this becomes a totally disconnected one. And the first one is just touching. So this converse part is not be true. That is the example. Now, suppose phi be a type 1 homogeneous hyphasis on X cross Y with attractor A. If it is just touching, then the product of the projection maps, phi 1 phi cross phi 2 phi is either just touching or overlapping. Okay, if phi is just touching, then the product will be either just touching, sometimes it may become overlapping. And let phi is equal to this, be a type 1 homogeneous hyphasis on X cross Y. If this projected one is phi 1 phi cross phi 2 phi is just touching, then phi is either just touching or totally disconnected. See the difference in these two theorems. Okay, if from here, if phi is just touching, this product is either just touching or overlapping. And here, if the product is just touching, then phi is either just touching or totally disconnected. The proofs are very interesting. You can go through the paper if interested. Now, suppose phi be a type 1 homogeneous hyphasis on X cross phi. Attractor is A. And if phi is overlapping, clearly the product of pi 1 and pi 2 are also overlapping. So in overlapping case, it is very clear. If phi is overlapping, so is the product. And of course, you know, these projection maps are also very important when we deal with applications. As I told you, especially in image, we're dealing with images. Generally, even though, you know, engineers and doctors generally won't appreciate the study of technical things with images, from my experience, what we have seen is this research based on images also produce wonderful results, at least theoretically, like collage theorem, for example. But you know, maybe in future we may find more refined versions, and that may be giving better results also. That's what I think. So these projections also are very, very important. So when there is an attractor in the product space, and in order to study the properties, better you project it in the coordinate, planes or lines, whatever it is, and study the properties of the attractor. That is what we are discussing in all these, previous few slides. Look at this. So the converse of this is not true. If phi is overlapping, then so is the product of the projections. If the product of the project is overlapping, need not be true that phi is overlapping. Look at this. So phi is this. Projections are available. Projections are clearly overlapping. Pi 1 phi is overlapping, and pi 1 of another one is pi 2 maybe. Right, that is totally disconnecting, but the original you can see it is not overlapping. It is totally disconnected. And now we will go to another section called separation properties of condensation hyphasis. Separation properties of condensation hyphasis. Now, a condensation hyphasis with condensation set C and attractor A is said to be totally disconnected if this is the property. S1A intersection Sj equal to phi for every I not equal to j in 0 M. Anyway, since there is no definition for condensation hyphasis, we provided that all. Okay. Now, a condensation hyphasis with the condensation set C and attractor A is said to be just touching. Anyway, there are some minor changes you will see after some time. It's just touching if it is not totally disconnected, and there is an open set O satisfying this condition. SIO intersection SJO equal to phi, and O is contained in the union of SIOs. Okay, as I told you, these are all similar to the other ordinary iterated function systems, as the circle connecting the vertices of the triangle. You know that S1 of triangle union S2 of triangle union S3 of the triangle, everything is inside that circle, right? So union of that is contained in O. Similarly, and there is one more, that is its closure of O minus union SIO is contained in C. So there is a additional condensation condition also. That is why we need to provide this one additionally. Okay. So that third last one is using the condensation set. Now, a condensation IFS with condensation set C and attractor A is overlapping if it is neither totally. Of course, this is from the classical version only. Yeah, you can see this. Look at this. This is your condensation set. And S1 and S2 are two different contractions. It is going like this. Okay. Look at this. Here we have two different functions. Here also we have two different functions. So that is it. This is okay. If it is neither totally disconnected, not just touching, right? You may look at this very carefully. Actually, depending upon these iterated function systems, the attractors are coming different. You can see that this is not this totally disconnected. You can see third one is overlapping and the second one is just touching. Okay, right. This overlapping is mentioned in the black dot thick lines. Right. Now, let X is and S naught, S1, etc. SM be a totally disconnected condensation IFS with condensation set C. Then there exists an open set to satisfying this condition. It's a theorem, actually. If it's a totally disconnected condensation IFS, we can find an open set satisfying this condition, and that condition involve the condensation set also. That's the advantage of this theorem. Look at this. That phi is a condensation IFS with condensation set C. If phi is totally disconnected, so is the corresponding homogeneous IFS, phi not also. But the converse of this is not true. We have example here. Yeah. Actual phi is Rx by 3x plus 2 by 2. And look at this condensation set is 1 by 3, 2 by 3. That's the condensation set. Okay. You can see that phi is, yeah, it is for the converse part, right? Corresponding homogeneous IFS is totally disconnected. First one is the corresponding homogeneous IFS, but phi is not totally disconnected. You can see the attractor here. Okay. Now, let phi this be a condensation IFS with the condensation set C. If the corresponding homogeneous IFS is just touching, then phi is either just touching or overlapping. That's similar to one of the previous results we have seen. Let phi be a condensation IFS with condensation set C. Phi is just touching, then the corresponding homogeneous IFS is either just touching or totally disconnected. Also is similar. Now let phi be a condensation IFS with condensation set C. If the corresponding homogeneous IFS is overlapping, then so is phi. Okay? If the homogeneous IFS is overlapping, so is phi. That's an advantage here. Okay? Now, product of condensation IFSs. The product of two condensation IFSs with the condensation set C phi and C psi, let us denote it phi cross I as the product, is defined as an IFS on X cross Y with condensation set C phi cross C psi. Look at the condensation set. C phi cross C psi will be the condensation in the product. Actually, since there were no definition for, once we have a condensation set in the concerned individual iterated function system, so how to take the product? The product also will have a condensation set. We take it as C phi cross C psi. And contractions as usual, Sij equal to Si cross Sj star. Okay. And this is how we define the condensation IFSs in product spaces. Now, look at this. Let phi is equal to this, y is equal to psi equal to this, be two condensation IFSs with condensation set C phi and C psi. Let A phi, Si, and A phi psi cross psi are the attractors of phi psi and psi cross psi. Then the relationship is clear. It's a very nice relationship. A phi cross psi is a function of S psi cross phi, where S is from X cross Y to X cross X are Fxy equal to Yx. That's an isometry. Okay? So A phi cross phi is simply F of S psi cross phi. So using an isometry, you can find, as you know, A cross B generally not equal to B cross A. And for the product IFSs, you can have a commuting mechanism using an isometry. Okay? In case of condensation IFS with condensation sets. Look at this example. Phi is this. There is a condensation 2.25.75. S1x equal to x by 2. S2x equal to x by 2. SI. SI, that's attractor. Fi, sorry. Fi is the attractor. That is simply, 0, 1. Similarly, for psi, it is 0.51 is the condensation. S1 is x by 2. And Si is 0, 1. So you can take the individual attractor. 0, 1 cross 0, 1 is the filled unit square. You know that. That's coming on this. A phi cross Si is coming on the left side. But A phi cross psi. Remember, that's an attractor actually. Okay, phi cross phi is the product IFSS. We will start with the same, that particular, that you can see the condensation set. So its attractor is going something like this. So in that way, but it will be preserved by an isometry actually. Okay, in two way it is going. Now let phi and psi be two condensation IFSS with condensation set C phi and C psi respectively. Let A phi, A psi, and A phi cross psi are the attractors of phi psi respectively. Then, this is interesting, A phi cross psi is always inside A phi cross A psi. Okay, so these are two condensation IFSS and their attractors are provided. So there is a relation between attractor of the product attractor and attractor of the product. Okay, let phi and psi be two condensation IFSS. Anyway, I will stop in 5 to 10 minutes. So let phi and psi be two condensation IFSS with the condensation sets. Of course, as usually, Fi, Si, Fi cross I, etc. are the attractors. Then in which condition they are equal? EQ, if you can model a tumor, okay, maybe at least maybe a picture of the tumor, something like A phi cross psi. I told you phi may be in the IFS you generated from the first scan, and SI may be the IFS you generated from the second scan. So you have two IFSs. This is a reverse problem. They're going back. So A phi cross psi. So actually, this is much theoretical, and that's why there are a lot of options here. And generally, as I told you, if you take the product of the images, you cannot expect the actual tumor. But in certain situations, it will be. So at least for certain kind of tumors, it will be true. Okay. So provided there is a condensation actually. Generally, there won't be any condensation for such items, but still, even we can even study about natural growth, for example. A tree maybe. Okay, tree is an example of an attractor of a condensation IFS. The trunk of the tree will be the condensation set, etc. So even for natural growth, we can apply this theorem. F phi cross I is Si cross Fi. If and only if both phi and psi are not optimal, phi is not optimal. Okay. Psi is not optimal and conditions are there. C phi is equal to A phi and C psi equal to Sa. There are not many conditions. Actually, it's not an if and only if theorem. It's only something like a proposition only. In these situations, this will be true. And there may be more situations as well. Now, suppose you have two IFSs, okay, and their product, everything is found, right? You take the projection. Projection of the product IFS is, suppose A phi, okay? Suppose then, then the projection of the first projection of the product attractor is A phi, and pi 2 is A psi, where pi 1 projection maps to first second respectively. In this case, if there are IFSs, condensation IFSs, then this condition also is satisfied. Now, suppose you have two condensation maps, C phi, C psi are attractors, then the product phi cross psi is optimal if and only if either phi or psi is optimal. Now, let phi is equal to this, psi is equal to this be two condensation IFSs. Okay, then A phi cross psi is strictly supercell similar if and only if either A phi or A psi is strictly supercell similar. So if one of them is strictly supercell similar, the product also will be strictly supercell similar in case of IFSs with condensation sets. Now, the last topic is separation properties of product condensation IFSs. Okay. Anyway, the assumptions are similar as usual. The product 5 cross I is totally disconnected. Here we need to discuss only about the, not about the attractor, only about the IFSs. 5 cross I is totally disconnected if both phi and psi are totally disconnected. Okay, look at the picture. The picture is for the other side actually. This is not if and only if. Phi cross I is totally disconnected if both are disconnected. Okay, the converse is not true. The converse is not true. Okay, you can see the attractor is totally disconnected, but the individuals are simply one is just touching, other is overlapping. You may see from the even from the picture, right? Okay, so the converse of theorem is not true. Now, finite powers of totally disconnected condensation IFSs are totally disconnected then as a corollary. And in this theorem, if the product phi cross I is totally disconnected, then the homogeneous IFSs correspond to phi and psi are totally disconnected. The homogeneous IFSs corresponding to these are totally disconnected. And here, suppose you have to, again, assumptions are similar. If both are just touching, then the product is never overlapping. It's an entirely different thing, actually. The product cannot be overlapping if both of them are just touching. Example is this. Okay. Just touching into just touching is totally disconnected in this case. So here, just touching into just touching is just touching. It's not overlapping. Okay. So these are two examples to substantiate that theorem. Product can be just touching even if both the coordinate IFSs are not. You can see this. If none of them are just touching, first one is overlapping, second is overlapping, but the product can be just touching. So there are a lot of magic there. Okay. So suppose you have two condensation IFSs like this. If the product phi cross I and the homogeneous IFS are phi naught and psi naught are just touching, then both phi and psi are just touching. Okay. And another result is if at least one of phi naught and psi naught, the homogeneous IFS correspond to phi and psi is overlapping, then the product phi cross I is also overlapping. And the converse is not true. You can see from this picture. The converse is not true because this is phi. Okay, this is the corresponding homogeneous one. One right side is the image of the first one, and the second is given below. You may go through this example properly. Another result says, suppose you have two overlapping condensation IFSs. Okay, then the product is totally disconnected. The homogeneous IFS correspond to phi, phi naught. Totally disconnected if phi naught is totally disconnected and an extra condition is satisfied. Similarly, it's just touching if phi naught is just touching and there is an open set condition to be, extra open set condition is to be satisfied. This theorem also is very worthy actually. You may go through the proof actually. It's not a straightforward one. And similar results here. See, phi is IFSs with the condensation set C. Attractor is type 1 if attractor is not equal to the product of the projections. Sorry, not attractor, it is that the condensation set C is not equal to pi 1 C cross pi 2 C. And each contact similarity is of the form SIXI is equal to SI1X, SI2X, where SI1, SI2 are contact similarities of X and respectively. Okay, so pi 1, phi, pi 2, phi, etc. are given. So here is an example. Since due to lack of time, I'm just I'll try to finish the presentation quickly. So similar examples you have already found before. So please go through these slides. So suppose it's a type 1 condensation IFS, attractor is A, then pi 1 phi cross pi 2 phi, its attractor is will strictly contain it. Containment is very strict in this case. And similarly, suppose phi is type 1, attractor A, then pi 1 phi cross pi 2 phi is totally disconnected. If it is totally disconnected, then phi also will be totally disconnected. The converse is not true. You can see, look at this. This is the product A pi 1 phi cross pi 2 phi. and this is the attractor of the previous one A. These two are the functions. So you can see that they are different. One is overlapping and another is not overlapping. Okay. And suppose phi is a condensation IFS. If phi is just touching, then pi1 phi cross pi2 phi is either just touching or overlapping. Similar result is there. Now, suppose it is type 1 condensation IFS with attractor A. If phi is overlapping, so is the product of the projections. And the converse is not true. Here we have an example. This is the attractor of this particular IFS, and this is the attractor of the, product of the projections, actually. Okay, so these are the contents of the presentation. As I told you before, major references are these three papers. This actually was my PhD scholar, and you may please go through them on different forms of similarity. Another one is weak self-similar sets. Anyway, only few things are taken from that paper, and separation properties of finite product of hyperbolic iterative function systems. So these are the major references. Please go through those papers if you are interested. And of course, as usual, we have all the major works by our famous mathematicians in my reference list. Thank you. So if you have questions, you can ask me now.
Thank you, Dr. Sunil. I am stopping the recording now.